Assalamualaikum and good morning. So we start our class this morning. So we continue what we learned yesterday. So it is about how to derive our continuity equation based on cylindrical or polar coordinates. So yesterday I just wrap up what we learned yesterday. So yesterday we derived our continuity equation but based on Cartesian coordinate. So I hope you could study by yourself and make sure that you could draw this diagram. So you could draw a square here. You could put value for input for x direction, value for input for y direction, and then output for x direction and output for y direction. And then you could use this kind of diagram to do or to derive your own continuity equation. Okay, continue. And then for continuity equation, it is actually can be derived for two types of fluid. One is compressible and another one is incompressible. Okay, so I hope you could you know how to differentiate between these conditions. So the compressible one, the equation must have rho, must have density, because the value of density is not constant. For incompressible, so you may neglect the value of rho, so because the density is constant. But be careful, the words neglect the density means that the changes of density can be ignored. The density is still carry certain value. It is not equal to zero. So, but the changes of density is zero, mean there are no changes between inlet and outlet. Okay, so that's what we did yesterday. And also yesterday we learned about the Navier-Stokes equation. So I hope you could understand how Navier and Stokes together derive the equation to represent the motion of one single particle of fluid. So we call that a Navier-Stokes equation. And Navier-Stokes equation has a simple terms, and also it has a very complex term. So, and then the way you could remember Navier-Stokes equation is by first remembering the basic shape, the basic terms of Navier-Stokes, which has capital D over dt and also contain the nabla. So, and then you need to remember, you need to know what is d over dt, capital D over capital dt, and also the nabla. Okay, then you could expand the Navier-Stokes. But it's okay. I think you may download these notes, or you could make your own notes by watching these videos. And today we are continuing our derivation on continuity equation, but we are using cylindrical coordinates. So cylindrical coordinates is actually based on this movement. So for example, we have one particle here. So, and then this particle is rotate like this one. So, and then we make assumption that the distance or the radius here is remain constant. So, mean this particle is moving in circular motion like this, but it's maintain the distance from the center point here. So, and then we take this particle. So we take this particle and then we could draw something like this. So I hope you could imagine from where this cube, it is actually not cube. This is because we have a radius here. So this is not cube, but this shape is actually come from this movement. Okay. So, and then we need to give terms, we need to give the distance in this one. So because this side is actually represent the radius, so we know that from the center point here to here, so the radius is r. So, and then the difference, a small difference at here will give us delta r, or in some textbook they just use dr. Okay, that's I hope you could understand that the r here means the distance from the center point to this one, and the r here is actually the distance of this one. So that's why when we want to mention the distance from here to here, so we just write as r plus dr. So we have the distance of radius here plus the dr of this one, and we have r plus dr here. So this is the axis of radius. So and then as I mentioned yesterday, so in polar coordinate, we represent the location by showing the distance of radius and also the location in terms of theta here. So from this diagram, we found that the distance here is actually represent the angle. So that's why for this distance, so we could calculate the distance here by using, okay, this is might be quite a confusion here, is delta. Delta here is just showing the angle. So means the angle here is, if the angle here is theta, and then a small opening here will give us delta theta. So that's why the total angle here will become theta plus d theta. Okay, but theta is the angle. So the unit of theta is actually the angle. So 5 darjah, 6 darjah itu adalah theta. So we need to calculate distance from the theta. That's why we use the unit of radians. And I think you already know, if we have a circle shape, we could calculate the distance by having r and d theta. So this is the calculation of by using radian and distance. So you have the total distance of this line. Okay, so means that the theta here is actually showing the opening here. Okay, so but to calculate the distance, you need to use the idea of r d theta. Okay, so d theta is here. So this is d theta, and the angle here is theta. Okay, I hope you could imagine that. So and then this is the z-axis. Okay, the z-axis. Why? Because we imagine that we have something like this one. So and then this is the r. Okay, this is the molecule that we are talking about. So and then the motion parallel with this one is actually the z-axis. So the z-axis will become the width or the thickness of this cube. So this is the z. So and then we have delta z here, dz. So that's why we show here as z plus dz. So I hope you can understand the distance in this diagram. So okay, it comes from this diagram. So and then this is another diagram to make sure that you understand the location of r. So this is the location of r axis. So and then this is the direction of theta axis, and this is the direction of z axis. Okay, so this is the relationship between this cube and also to this axis. So I hope you could you could imagine from where this cube come from. Okay, so we start our calculation about continuity equation, and we are still using the same idea that we explained yesterday. So we have mass flow rate at inlet minus mass flow rate at outlet, and it must be equal to dm dt, means the changes of mass according to time inside the system. So and then the mass flow rate here can be calculated by using the idea of rho, A, and V, where the rho is the density, the A is the cross-sectional area, and V is the velocity of fluid. And please make sure that you really understand how to calculate, how to take the cross-sectional area. It must be perpendicular to the velocity. Okay, so it's quite a long calculation. So to make sure that we could have easier view for this one, so I separate this calculation according to its axis. So means that as you know, here we have r axis, mean inlet at r and also outlet at r, So, and then we have inlet here for the theta axis and also outlet here for theta axis. And then we have inlet according to Z axis and outlet at the Z axis here. So we have three axes, so we have three inlet and we have three outlet. So we may calculate all of them, but might be you have difficulties to write all the terms in your A4 papers. So to make sure that you really understand these and you have a good enough space to calculate this one. So I would like to propose to you, why not we calculate this one according to its axis. So for example, we try to calculate what is the flow rate for the direction of radius. So for VR. So here, VR means that we are calculating the inlet for this one and also outlet for this one. Okay, so the inlet here, because we need to fulfill what is the value of mass flow rate at inlet and mass flow rate at outlet. So for mass flow rate at inlet, so we could write as this one. So we have rho r d theta dz and VR. So here, please remember that mass flow rate here is equal to rho A and V. So rho here can be written as rho in this one. So, and then the velocity here, because the velocity here is the velocity component, the component velocity according to the R axis. So we write as VR. So, and then A here can be write as R d theta dz. So what is R d theta dz? As we know that the distance here is R, okay, and then we could calculate the distance of this curved line here by multiplying R and the angle. So we have R d theta because the theta here is d theta. So R d theta means the distance of this line, and the Z here, dz here is actually the height, the thickness of this cube. So the multiplication of R d theta here and Z here will give us a cross-sectional area. So the R d theta dz will give us the value of A. So R d theta is the distance of this one, and dz is the thickness of this cube. So I hope you can understand here why we take R d theta dz. So and then we minus here, okay, with the mass flow out that occur according to the R axis. So again, the calculation is remain the same. So the m dot here is rho A and V. So the V here, okay, can be written as V. Okay, okay. The explanation is same with the Cartesian coordinate because we are derive an equation that suit for compressible and incompressible. Means we try to derive equation that can be used for both. That's why we make assumption here that maybe density and velocity will change. So the remain unchanged parameter is only the value of A. So the A here is R plus dr d theta dz. So R plus dr means, so the distance from the center point here to this one. So this is R, and then we add with delta R, so it will become R plus dr. So this is the distance from the center point, R plus dr. D theta is the angle of this one, the opening of this one. So you must understand that the bigger the value of R, it not changing the value of d theta. So nilai angle tetap sama walaupun nilai jejari semakin bertambah. Okay, yang ini saya harap awak dapat faham. So jadi means walaupun jejari telah bertambah, tetapi nilai angle di sini tetap sama. So R plus dr d theta will give us the distance of this line. So and then we multiply with Z here, so that we multiply with the thickness of this cube. So means that we could get the cross-sectional area at the outlet. So we have an A here. Okay. So and then, okay. So for here, okay, so we have rho and VR, and then we add with the differential, uh, with the partial differential term. So we have del over del R with rho and VR dr. So this is, I think you already learned about the partial differential, because we assume maybe the additional value or the changes is occur apart from the density and also apart from the velocity. So that's the del here will become, okay, the del here, so we have d del over del R for rho and VR. So it maybe can be changed into d rho over dr, and we constant the value of VR plus with dVR over dr with the constant of rho. Okay, so I think you already know how to expand the partial derivation. So this is the most important idea that you should know before you could derive all the things. So first, you make sure that you could understand how to write this one. So this is actually the mass flow rate at inlet minus with m flow rate at outlet. So you know how to calculate this one. The rule of thumb equation is m dot is equal to rho A and V. Okay. Okay, I hope you could write this equation, and then what you need to do is you need to expand this one, so you may have this kind of equation. So and then after this you will get yeah, you need to expand the equation, and then you may neglect something that very small. So here, so normally we could say that dr times dr is a very small term, so we could assume that the value is equal to 0. So after you applying this assumption, you will get this term, okay, and then you could simplify this term into this one. So means that the mass flow rate at r direction is negative del over del r rho vr dr d theta and dz. Okay. So if you don't have any idea how to convert this one, you may change this. You may expand this term first, and then you could say that it can be combined as the partial derivation of this one. Okay, so for this one, I think you already know you have three variable. So means you could write is d rho over dr, and the constant is vr and r, and then you could plus with dvr over r, and the constant is rho and r, and so on and so forth, and then you plus with dr over dr with rho and vr as the constant. Okay, that is the idea of partial derivation. I hope you could make some study for this operation. Okay, I'm not showing you the detailed calculation because every semester student could derive this by themselves. So I hope you could derive it by yourself too. So after you derive all of this, you could get that the m dot for inlet minus m dot for outlet is this term. So and then we calculate the value of mass flow rate for the z-axis. So the z-axis is the inlet is here and the outlet is at the top. So the inlet is rho vz r d theta dr. So again, so I can make it faster. So m dot is equal to rho A and V. So A here is r d theta dr. So I mean r d theta dr is the distance of this one. So and then the dr here is the distance of this one. So it is true that this object is not a cube. But to simplify this calculation, we just assume that the curve of this line is not too obvious because we are calculating very small element. So we could assume that the area is still correct if we are using the calculation of x times y, like a square area. So we just multiply the r d theta, the distance here, with the dr here to get the value, the cross-sectional area at inlet. So and then rho is rho, and Vz is the V, the velocity at Z axis. And this is the term for the outlet. So the R d theta dr is remain the cross-sectional area for the outlet here. So and then we make the derivation, the partial derivation, like this one. So and then you may expand this equation, and finally you could get this term. Okay, so and then we calculate the third axis, which is the direction of theta here. So the direction of theta here means the inlet is here and the outlet is here. So we use m, rho, a, and v. So dz dr here will represent the value of a. So dz means the distance of this one, and the dr is the distance of this one. So the multiple of the dr and dz here will give the cross-sectional area for inlet as well as the cross-sectional area for the outlet. So and then the rho and v theta is rho and velocity here. So if you expand this one, so you will get the value of this term. So you have negative del over del theta, rho v theta, d theta, dr, and dz. So and then the fourth one, because our basic idea is mass flow rate inlet minus mass flow rate outlet, it is equal to dm dt. So the fourth calculation is actually to calculate what is the dm dt. So we know that the mass, okay, it can calculated by using rho mass over volume, and then we could write as mass is equal to rho times volume. So I write here mass is equal rho times volume, and volume here can be calculated by using this idea. So volume is r d theta dr dz. So this is volume. So r d theta mean, so the distance here r, and this is the d theta. So we get the distance for this side. Dr mean the distance from this side, and dz is the depth of this cube. So again, because we assume this particle is very, very small, so we could assume that this particle is actually a cube. So we could calculate the volume of this particle with the idea to calculate the volume of a cube. So we just multiply r d theta, dr, and dz to get the total volume. So now we have the dm dt. It's now equal to del over dt for rho r d theta, dr, and dz. So then what we need to do is we need to substitute all the terms that we get into this equation. So we have m dot inlet minus mass flow rate at outlet equal to dm dt. So we substitute all these three equation that we calculated previously, and we substitute the dm dt with what we have here. So and then we could say that we always have d theta dr dz. So dz, so we divide all the term with d theta dr dz, and finally we could get this term. So and then here on the right hand side, you will have del over del t, rho, and r. So and then we could calculate as rho dr dt plus r d rho dt. So and then here again, mathematics, it's only not equation that we need to put numbers and solve it, but sometime in stage of derivation like this, you need to really understand what you are calculating for. So for example, in this situation, when you expand these terms, you will get rho dr dt. So here dr dt means the changes of r depend on time. So because usually in mechanical engineers, the value of radius of certain element, mean radius of our pipeline and so on and so forth, is remain constant. So means that the dr dt here is equal to 0, because our machine, the radius of our pipe and so on and so forth is not changes along the time. So mean it's remain constant. So means that the dr dt, the gradient, okay, the changes of r over dt, the changes of r over time is not changes. That's why we assume dr dt is equal to 0. Okay, so I hope you can understand this one. So, and then what we do here is, okay, we rearrange all this term. Okay, so and then we will have this one. And after we expand all the terms, because we have the partial derivation here and so on and so forth. So when we expand this one, we could write as this one or this one. So this is, if we bring the r here, we divide all the term with r, so we have 1 over r here. So that is the difference between these two equations. So this equation, so this is the compressible equation of continuity in cylindrical polar coordinates. So this is the overall or the general equation for polar coordinates. So why this become the general equation? Because in this equation, it can be used for both. Mean can be used for incompressible and compressible situation, because we have density parameter in this equation. So, and then we try to simplify this, because later on we will focus on two-dimensional incompressible fluid. So two-dimensional means there are no value, there are no parameter for z-axis, and also the incompressible means there are no changes in density. So we neglect all the terms, so the terms will become like this. So this is the basic idea. So I hope you could expand this one. So, and then you could neglect all the value. Okay, for example, here we have the partial derivation del over dr, vr, and r. So if we have del over del r, vr, r here, so we have it's equal to dvr over dr with r constant plus with dr over dr with vr constant. So, and then the dr over dr here will equal to 1. So, and then we have vr over r here. That's why it becomes vr over r here, because we have another r here. Okay, so I hope you could try to solve this equation, because finally make sure that you need to have this equation to become the continuity equation. But in some textbook, if you have textbook from other authors or other company, so it may write the continuity equation for polar coordinate something like this. They are using u prime as ur, and they will use v prime as u theta. Okay, so they just want to use the same terms with the Cartesian coordinate, which is u and v. So to differentiate between the situation is u prime and v prime. So this symbol, this apostrophe, is called a prime. So you have u prime and v prime. Okay, but both are correct actually. But the most important one is to make sure that you could write this one, you could write this equation from the basic diagram. So means that you need to write your own diagram like this first, and then you expand, you write down which one is inlet and outlet, and then you expand the terms, and finally you need to get this term as the continuity equation for polar coordinate. So you may write like this one, or you may write like this one. Okay, so as the conclusion summary for the continuity equation, so this is the Cartesian, this is the continuity equation for Cartesian coordinate, and this is the continuity equation for polar coordinates. So this is for both for compressible and incompressibles. That's why you could see the terms there. The value of density is still remain in the equation. So, and then for the Navier-Stokes, okay, for cylindrical coordinates or polar coordinates, so we reserve the explanation of the Navier-Stokes equation because it takes a long time. So, and it is, we exclude it from our syllabus because we have r-axis, theta axis, and z-axis, and all of them need to be derived separately actually because there's certain reason. So that's why in this situation, we just hope you could remember the Navier-Stokes equation for polar coordinates. So again, they're still using the idea of the d over dt here. So the mathematical expression and also the nabla. So nabla, as I said, it is you could have nabla square and also you could have a single nabla. So if the for single nabla here, so you just make the power here into 1. Okay, so that's the idea. So and then okay, so I hope you need to remember all of this. So we have a 3-axis. So we have the r-axis, the theta axis, and also the z-axis. Okay, so and then as I said, we don't show you the derivation for polar coordinates because you need to do this. You need to do that axis by axis. So because if you see this, the value of this one is not same. The value of r axis is not same with the theta axis, is not same with the z axis. It's slightly different. So I hope the value of d theta and nabla also will a little bit different. So that's why we're not showing the derivation, but I try to make sure that this equation is given in as appendix in your test or your final exam later on. But that's not a promise. So I hope you could understand this. And the best one is you need to understand and you need to remember and make sure that you could write the Navier-Stokes equation for polar coordinate as well as Cartesian coordinate. So this is the Navier-Stokes equation for r-axis again. So this is for theta axis and this is for z-axis. Okay. So and then this is the notes because sometimes in many textbooks, so they will give you a few terms. Sometimes they will give you this kind of this term, and sometimes they will give you the term of this one. Okay, so sometimes they will use this one and sometimes they will use this one. So actually this both will represent the same things because if you expand this one, okay, as I show here, so you will get this one and then you could rewrite this one by neglecting the value of r here, okay, by cancelling the value of r, so you will get this term.